So my name is Colby. I'm going to be doing a demo of the immersive audio that you can produce right now with your browser using the JavaScript Web Audio API. It's a little known feature of JavaScript. It's not used across all of the internet, and it's just one of my favorite things that I've ever discovered. It's like in some video games, like Tunic, you discover that you have always had the power to do something, but you just didn't know about it. And I always love that feeling. So this is exactly that. So way this presentation is going to go, I'm going to give you some setup for the project that I have in mind. We're going to talk about the concepts behind the JavaScript Web Audio API. Then we're going to get into the actual live coding demo, and then we'll talk about the results, things that you can do in the future, and cool ways to use this. So, Paris is nice, probably. I mean, look at that picture. It's that looks like a nice day. I've never been there because I am deeply uncultured, so I don't know French or really any other foreign language. It's really difficult to also travel whenever you have a baby, which I do. And long flights are made even longer when said baby comes with you. So for all of those reasons, Paris is not within my grasp, it feels like. But I thought, what would be kind of nicest if I could simulate it, if I get something kind of close, you know? So let me describe to you my dream afternoon. It's a mid-afternoon in October. Maybe it's like brunch time. Maybe it's like sort of in that like late morning, early afternoon window. I'm eating some French bread. It's nice and hot and it tastes delicious. And I'm listening to a sound check outside of the Athene Theater. You can see that there are there's some salt baying of some accent marks over some of those E's. I don't know how to pronounce that. Again, refer back to slide 1 with deeply uncultured. But this is like a really nice looking theater, and it sounds really good. It's a relatively well-known theater inside of Paris. So imagine in this area, this is kind of a square. There's a cafe that's actually like almost next door. So imagine like I'm sitting outside, I'm eating my nice bread. It's a nice afternoon, which is the only reason why I'm outside. And so if I want to simulate that, I want to try to give you that experience if you close your eyes and you just listen to the audio. So I want to try to create this immersive audio experience to sort of transport me and you, the viewer, there. And we're going to be doing this together as well. So if you want to make it sound like you're listening to the soundtrack of, I don't know, the Pearl Jam, outside of some grungy bar in 1993 Seattle, whatever, you can do that. I will give you the tools to enable you to have your own wild fantasy, and you'll be able to share this experience widely as well. It's in the web browser, right? So that's like there's no installation required. Everyone has a web browser. You can just go to a website. And because this is already built into JavaScript, there's not going to be many version conflicts here, right? So let's get into the concepts behind JavaScript Web Audio API. Basically, everything is inside of an audio context. Inside of those audio contexts are a bunch of nodes. You can think of this like a DAG, which is a directional acyclical graph. It's a programming concept, but effectively it means that it's a graph that moves from like one node to another. It can split, it can rejoin, but it cannot loop back on itself. So imagine this is effectively a DAG. There are many inputs to this. In particular, for the Web Audio API, you can have as many inputs as you want. There's only one output. That one output goes to your headphones. There's a couple of exceptions to that, but I mean, we want to hear this sound, right? And yeah, nodes are like sort of the base concept. They're your protons, your neutrons, your quarks, I guess. Sorry, I'm using science terms. The latest science terms from 1972. I apologize. And yeah, so there's a bunch of different inputs that you have. You can affect those inputs in a bunch of different ways, and then you pull them all together to put them out to one destination. And so there's a bunch of different node types that you get to experiment with inside of the JavaScript Web Audio API. For inputs, we've got tags, like if you have a media tag on your website, any of the media that's in there you can get, which means local files, that means streams, math even. If you have a function that defines like what a sound sounds like, a square wave generator, a sawtooth generator, great for simulating like older game consoles, NES, Genesis, stuff like that, and user media. So if you want to actually apply some of these effects to your voice, you can also do that. Anything that can input, any way that you can feed audio into your web browser, you can use with the JavaScript Web Audio API. And there's a whole bunch of different processors as well to modify the audio input and then output it. There's filters, panners, reverb, there's spatial stuff. So you can actually do 3D audio and simulate being inside of a room. We're not going to get that technical today, but we'll touch on the rest of them. Don't worry, I'll get you there. There's the output, right? You can take multiple audio sources and then output all of it into whatever the browser is connected to, which in our case is just going to be our headphones. And then there's a couple of miscellaneous operators. There's an analyzer, so you can pipe that audio output into an analyzer and say like, hey, at this point, I want to examine what the audio sounds like. Yes, that waveform pleases me. You could also have user-defined nodes. So if you wanted to define a node in which you took input audio, and for every number that was given to you, you just added 2 to it and output it, you could do it. I don't know what that would sound like or why you would want to do that, but you can. And you can also separate the channels. So if you want to do some like really funky, weird stuff with like, yeah, your right ear is like hearing the audio, I don't know, like low pass filtered, and your left ear is hearing the audio high pass filtered. I imagine that would be really uncomfortable to listen to, but go for it. Like the sky's the limit here. So let's get into it, right? Let's get some code. So make sure that you've got, you're in your repo. You've opened up the code base from ! code along, and you're inside of your terminal window, and you do Python -m HTTP server or Python -m simple HTTP server if you're on Python 2, and come along with me. So if you're to open up localhost 8000 right now, this is sort of what it sounds like. In fact, I'm going to make sure that I've got my audio here because if I unmute this, it's very loud. So this is just a song. This is, I believe it's called, God, I should have looked up how to pronounce this because it, let's have a little fun pronunciation guide with Colby. This is Gymnopede. That's, refer back to slide 1. Uncultured. So this is like a relatively well-known song. This is like one of those Incompetech joints that is copyright free. So Gymnopede. Yeah, it's like that. Probably. So right, this audio is pretty loud. It's loud enough, in fact, that I'm going to come back to my window here and I'm going to mute it. I'm going to turn my volume back up to where it was. And now let's take a look at our code. I'm going to go through sort of the base setup of what this repo is, the code that's already written, and then we're going to start getting into the actual meat and potatoes of this. So I have a function here, add web audio API, which will, this is what we'll be modifying. You can see that in here, I am snatching the audio from a media element source. If you take a look at the HTML, we've got our audio tag right here. Above it, we have a canvas called visualizer, and then we're linking out to our main.js. In here, I've just defined the static file that is going to be associated with the source for this audio, but there's no reason you couldn't just go to like a text box and hit submit and replace that value in JavaScript. You could totally do that. All of this will still work. So I've grabbed that source node and I've created an analyzer and I've hooked that analyzer up. So up at the top, if I unmute this, you will see that I had to turn it back down. You'll see that like I've got a visualizer here. So down here, I have this setup visualizer. There's a bunch of stuff here that you don't really need to know about. Effectively, what the visualizer inside of the web audio does is it takes the audio that's being input and it outputs one of two things, either the raw waveform in the time domain, or it outputs the frequency response. For us, we're looking at the frequency response. You can see that right here. I'm looking at frequency bin count, and I'm grabbing all of the things that I want to get the byte frequency data. Effectively, what this does is this allows us to visualize how low or high the audio is. So we can see what we're doing with our filters. So here you can see that this song, anytime you hear like the higher parts of the piano, you can see the parts of the visualizer on the right side of the graph get a little bigger, right? So the low parts, they're all bass. So yeah, that's what this particular section is doing. I've got a create slider function just that we can play around with creating nodes inside of the JavaScript Web Audio API and tie them to sliders, and we don't have to go through the rigmarole of create this element, create an input. I wanted to make sure that this also didn't have like a framework associated with it, so you didn't have to like download React tools or link out to anything weird. This is all vanilla JavaScript. And then there's one more thing, which is get impulse buffer. I will talk about what that is after a little bit. I was gonna say Tarantino you. I'm gonna reverse Tarantino you on this one. So, all right. And just like that, my timing is impeccable. The song is over. I'm very impressed with myself. I hope you are too. Okay, let's take a look at what we've got here. Inside of Add Web Audio API, we have our source node. Again, that's where the audio is coming from. And we've connected it to the analyzer, and then we've connected that to the destination. So the analyzer is just there in the middle to be able to display stuff, and then it outputs the audio unchanged, and it hits the destination, which is our ears. So first thing that we want to do, again, this is awfully loud. So we want to create a gain node. Gain nodes control the audio level, the amplitude of the audio, so how loud the thing is. So let's go ahead and create a gain node here. So here on line 10, I'm going to hit enter a couple times just so we can really clearly separate where we're doing stuff. And I'm going to go const gain node is equal to, keep in mind, everything spawns from the audio context. Audio context is a special variable here inside of JavaScript that allows you to create everything inside of the JavaScript Web Audio API. So we want to do audio ctx, which is the name of our audio context variable, dot create gain. So now we have a gain node. And in order to control that gain node, what we want to do is add a slider here, right? So we're going to use our create slider function. We're going to go const gain slider is equal to create slider. And this takes an ID, text label, min max, current value, step, and parent value. So the ID of this is going to be gain. The label that I want for this is the word gain, but with a capital G because, proper punctuation. We're not monsters. The minimum here we're going to say is 0. This means that it's completely muted. Don't want to hear the sound. And the max here, just for kicks, is going to be 2. If you wanted like audio in the JavaScript Web Audio API is a number. It's represented by a number between 0 and 1. They're all decimal numbers. And so 1 is like, you could think of it like percentage of audio. I think it's actually, yes. So it's 0 to 1 here. If we give it a value of 2, that will double the amplitude. So that will make it twice as loud. Don't worry, I will not be exercising this, but I did just want to show off that you can totally do that. Current value, I'm going to set to 1. This is just like, this is how loud it should be by default. And in fact, because it's so loud, I'm going to just decrease that to half. Our step here, every time that we move the slider, how louder should it get? Or what should our current value move up by? In this case, because these values are so small, we'll do 0.1 or 0.01, and we don't need a parent element. So great. So now we'll just say gain slider dot on input, This is going to equal to, we're going to do an anonymous function here. So this is to say, hey, whenever this gain slider moves, I want to take the value from it and I want to plug it into the gain node. So I want to say gain node dot, and if you're in any sort of like IDE that knows stuff about JavaScript, you'll see a bunch of things here, right? We've got functions like connect and disconnect. We've got number of inputs, number of outputs, channel count, blah, blah, blah. The one that we're interested in is gain. In this case, and then gain has some stuff in here like a default value, a max value, a min value. So if I wanted to set that max and min inside of this gain node, like with these properties, I could totally do that, but we're going to just go ahead and do value is equal to gain slider dot value. So now we'll save that and then let's refresh. There's our gain slider. And if I unmute, well, that's weird. Gain node's not doing anything. It's actually not weird at all. Because despite the fact that we created a gain node, we haven't put it into the chain down here on what is now line 18. So we have our source node, it connects to an analyzer, connects to our destination. What we need to do is connect the source node down here to the gain node. And that will get us there. So now this gain node is inside of the chain. If we refresh it and I unmute it, it's the volume's completely gone. Turn it up a little bit. Gets a little louder, gets a little louder. Turn it back down. A-okay. So far, so good. Everything's sort of making sense. Can I show the last line of code again? Yes, I certainly can. So this last line of code is to set the value of gain node dot gain dot value equal to the value inside of gain slider. So whenever you change a slider inside of JavaScript, it has a value called value that gets updated to wherever I think it's called the thumb on the slider is. So some position between this min value and this max value. So we've got this gain node now, and we can now listen to this music without blowing our eardrums out. So let's start to do some fun stuff, right? Let's do some let's get into some weird things. Like in particular, the one thing in order to sort of fulfill this fantasy of like sitting outside of this cafe is sitting outside in this cafe is if you hear someone playing music or any amount of audio that's coming through a building, the building actually acts as a low pass filter. So the bass will reverberate through the walls and you can hear that bass. The high frequency sounds will not. So if there's like a clear line of sight to like where somebody is, you can hear more of the higher frequency stuff that's coming out of it. And the lower frequency stuff will be more difficult to hear. If they are on the other side of a wall though, those low frequencies do come through the wall. So that's what we're going to be doing. We're going to make a low pass filter here. So we're going to do const low pass node is equal to audio CTX dot create biquad filter. There's many different types of filters out there. Biquad is just one of them. With this, you can create low pass filters, high pass filters, band pass filters. Band pass is like anything between these two frequency ranges. We should listen to that. Notch filters, exact opposite. Anything between these two frequency ranges, I don't want to hear. And sort of the biquad refers to how quickly the audio rolls off in that spectrum. So, if you say, I don't want to hear anything from 500 hertz to 510 hertz, at 501 hertz, how much is that rolling off? Is it 0? Is it close to 0? What's the difference between 499 and 501, right? So this is biquad, which means it's a second order filter. It means it rolls off a little faster. There's more science to get into there, but this is not one of those streams. I just come to wish you good luck. Thank you, Fee. I appreciate it. So low pass node dot frequency dot value. We're going to set this by default to 20,000. I'm keeping this here so that like I have this line here specifically so I can tell you that whenever you're like listening to stuff audibly with your ears, it's going to be in the frequency range of approximately somewhere around like 15 hertz up to 20,000 hertz. Anything higher than that, it's very difficult for humans to hear, especially older humans. You can sort of get up into like the 21,000, 22,000, 23,000 if you're like young and your ears are very good. But 20,000 is about as high as we really need here. So we're going to say low pass node dot type. So this is where we fill in the type here. And this is where all of those different filters that I mentioned are. There's all pass, band pass, low shelf, high shelf, peaking, notch. All these things you can set here. We are interested in low pass. So we now have a low pass filter. Let's do the same thing that we did with the gain slider, but we're going to do it with low pass slider, right? So we're going to create a slider. The ID is going to be called low pass. The label is low pass. And now this is awesome stuff. Thank you, Steve. I appreciate it. We're having a good time here figuring out the JavaScript Web Audio API. So for my low here, I'm going to set the minimum to 0. And then here, I'm going to set my high to the highest human frequency, right? We're going to set it not 200,000, close. We're setting it to 20,000. And then our current value, we're also going to set to 20,000. We're going to start off with not hearing anything different in the audio. And my step here, I'm going to say 1. Again, this is a very large audio range or a very large value range, 20,000. So having a step of 1 sort of makes sense here. And then we need to do the same thing as we did up here with the gain slider, set it with our on input. So we will copy the low pass slider in here, but the value is going to be a bit different. So we're going to go to low pass node dot frequency dot value. So gain node has a gain property with a value. Biquad filter has a frequency property with a value. So that value is going to equal to our low pass slider dot value. And now remember, we have to hook it up into the chain. So let's go ahead and do dot connect of low pass node. So if I refresh, there we go. I can turn down the volume here a little bit. And now I want you to pay attention to the visualizer. You'll be able to hear it audibly for sure as well. In fact, I'll turn it up a little bit. But the visualizer will also show this. Can you pause in the low pass code for a sec so I can catch up? Absolutely, I can. So watch this. As I decrease the low pass filter slider, frequency as a range is sort of like a little exponentially in that like your like lower stuff is kind of crammed together as far as like hearing goes. So let's take a look at what this does visually. The lower that I get, you see these highs are diminished. Keep going. There it goes. Pop it back up. So right here, this really starts to sound like it's on a wall over there, right? Like this really starts to sound like I'm listening to, like this audio is muffled. I'm listening to this audio through something. I feel so someone's explaining something profound. You got it. The JavaScript Web Audio API is life-changing. What can't it do? People have been saying more and more it can do anything. There's nothing it can't do. So we'll keep that on low while you guys catch up. And while you catch up, fun fact, this frequency value here, we don't actually have to set here. This is the default value. We set this to be like the initial value of it. And then we're overriding it here. So as long as you like change the value of the low pass node, it's fine. It works. Just, you know, keep that in mind. Just, yeah, let me know whenever you've caught up, and we will continue. One of the other really cool things that you can visualize with this, or one of the other cool things that you can do with the visualizer, is if I had inside of my index, if I had another canvas to draw on, I could actually have a second visualizer that connects at every point along this chain, right? So this could be the source node connects to an analyzer, then it connects to the gain node, that connects to another analyzer, that connects to a low pass node. Like, I could chain them like that and have a big list of at what stage each visualizer is, and you could see the audio differences. I'm not doing that because it's a little intensive to create a bunch of stuff and have it visualized like that, and it's a little weird. So, but that's totally something you can do. There's nothing to stop you from doing that. And one other really fun fact is that because we are looking at this music inside of the frequency domain, you actually will not see a difference between the source node and the result of the gain node, because again, all we're doing is playing with the amplitude. That's exclusively in the time domain. And when I'm talking about time domain, frequency domain, I'm talking about like, the way to think about it is, if I'm to look at here, if I open Audacity, I have Audacity open for this particular song right here up top. If I'm looking at, this is the time domain. This is what this actual waveform looks like in time. So at, 0.05 seconds, this is the value. At 0.051 seconds, this is the value, and so on and so forth. And playing that through your speakers is what audio is. If instead I took a slice of this audio, so the audio from 0.05 seconds to 0.051 seconds, and I put that into the frequency domain, that's what we're seeing inside of the audio visualizer up here. So each of these bars represents a rough range in sort of 0 hertz up to around 20,000 hertz. More or less caught up? Excellent. Great. So let's go ahead and move on to the high pass part then. The high pass part, you'll be pleased to know, is actually gonna be a copy and paste of the low pass part and changing some variables. So that'll be pretty fast. So if I want to filter out some of those high pass filter, some of those high noises, right? Let's say that I had a different use case for this, right? Like, you're down a very, very long corridor, and I can you can hear sort of like cymbals and stuff, but you can't hear those like big, I don't know. Let's say that I'm in a high school band hall. It would be difficult to hear the tubas maybe, but it would be very easy to hear the cymbals. So this is what a high pass filter can do. It only lets you hear the higher pass stuff. So let's add that in here. I just copied and pasted everything up here, and we're just going to be changing this from low pass node to high pass node. High pass node, on the other hand, the default frequency here should be 0, right? Because again, both of these are meant to be filtering out audio, and we want to control how it does that. So because high pass lets everything above a certain frequency pass through, we want it to be as low as possible. That way it allows all possible values through. So we go ahead and set that to 0. We say, hey, this high pass node, bam, this is high pass. Now we have this low pass slider, surprise, high pass slider. And then we name it the exact same thing, high pass. And the word high is here now. Here, so we still have the same min and max, right? Still the frequency range of human hearing. We are going to set this to 0 though. Again, the default value here, we want this to be where it's not doing anything to the audio. So now I put that high pass filter in, and there we go, and high pass node. So Exact same thing, right? Whenever the high pass slider moves, we want to set the frequency of the high pass filter. So the higher up we go, the higher up that frequency is going to be. So we now just have to connect it inside of our chain. So we'll do connect of high pass node. And let's refresh. So this is the bass sound, right? Let's start increasing the high pass filter. Immediately you will notice a change because most music has like a lot of really nice basses in it. Start coming up. Oh, did I not add in the high pass node? No, I did. Is there an issue here? Aha, yes. High pass slider dot frequency. I put in the wrong variable here. Haha. Thank you, JavaScript console. There we go. So immediately you'll notice an effect. Value being assigned is not a finite floating point value. Okay. That's interesting. Let's turn down the gain here. Ah, yes. I put in the wrong values in two different places. Totally my bad. Okay, there we go. There you go. So take a look at that. And immediately, with the low pass, it took a long time to get down there, remember? To hear any amount of audio difference here, it took a long time to get down. Here, all of that bass is just immediately gone. And the cool thing that you can do is you can use a low pass and a high pass in combination to make a band pass. So if I decrease this low pass, you can see that now there's only that band in the middle that's going. And in fact, if I go low, it's all gone. Because the high pass filter is taking care of filtering out the highs. You can still see, again, that there's some frequency response there, right? And you can still hear it. And that's because we're close to that cutoff frequency. Again, these filters are not like cliffs. It's not just like, oh, I got to that frequency, no more, shove it away. The further away you get from that cutoff, the more your amplitude is decreased. So as we increase this high pass filter, this is effectively muting it now, right? Because we're so far away from that cutoff. And if we keep going, it's all dead now. So very cool. We're not going to be using the high pass filter for our very cool France fantasy, our France to see, if you will. But it's kind of a fun thing to show off, right? Like being able to do this like cool kind of bandpass thing is like, oh, it makes you feel like you can be doing anything with the audio, which I'm here to tell you, you super can. All right, so are we all caught up? Do we have any questions or anything? Otherwise, we're going to move on to my favorite part of this. Caught up and very cool. Awesome. Love that. A weird equal ruined my life for a moment there. I'll get you. An equal sign. All right, so we're going to talk about reverb now. I told you, get impulse buffer would come back at some point. So, what is reverb? Reverb is, you can think of it whenever you're in a room and you're talking, your voice sounds different if you're in a room that it has a lot of carpet, has a lot of like fabrics and stuff in it, as opposed to a room that has a bunch of flat walls. And that's because your voice is bouncing off of those surfaces and hitting your ears at different times. That's what reverb is. Reverb is effectively the frequency response of a space. So frequency is like a really interesting to play with, and we're going to use that with this impulse buffer. Let's start off and do const reverb is equal to audio ctx dot create. There's no reverb. That's because it's inside of a convolver. So, convolution, no longer exclusive to Kingdom Hearts. Convolution is a mathematical operation, and I found a graph that will demonstrate this sort of the easiest way that I can think of. If we have two signals, if we convolve them together, that's taking one signal, running it over a second signal, and measuring the response as a result. If those signals don't overlap, there's no output. When they overlap, they either constructively or destructively interfere with each other, like waves in the ocean, and then they produce a result. So, take a look at this GIF. Input signal F is just a square, just up to 2, down to 0. G is a little triangle boy, right? What we do is we take the impulse response, which looks like this, and we turn it, because that's how it works in math, and we run it over our input frequency here. You can see at 0, we take a look at the response. The value of our impulse response at 0 is going to be 1, and this is 2, right? So that's going to jump up to 2. And then as it continues, this goes down, right? It's a triangle. It goes down. But it's not just the leading value here. It's now the leading value and the next value. So it's 1 and like whatever this is, 0.9, we'll say. So that's 1 times 2, which is this value. I guess the value that's here. And then 0.9 times 2. And then you add those together. So what ends up happening is as these signals run over each other, they build up. And then as they exit each other, they sort of squash back down. And the shape of the signal that pops out sort of looks like this. So it's like a combination of those two signals. So why did I tell you that? What does this have to do with reverb? That's basically what reverb is. Again, this is the sound of being inside of a room. It's simulating the audio hitting a wall and coming back to your ear at a different time. So this is like this triangle being going from like we're speaking here at time 0, and then at time 2, a little bit of our voice is hitting us again from, let's say, like the wall that's like the furthest away, or this like close wall, or some like chair in here, right? Like your sound comes out in all directions. I mean, it comes out from here, but then it bounces off of things in a bunch of different directions in a very cool waveform. And then it'll eventually come back to your ear at different times. So if I take a look here, that's the reverb that you hear inside of a room is defined by something called an impulse response. That's what this is. This bottom audio graph here is the impulse response inside of the Athene Theater. So what someone did is they set up a microphone and they went inside the theater and they clapped. And this is what that clap sounds like. So that's what it sounds like. Now I want you to notice that this has a very large response at the front. And then as time goes on, again, take a look at our time scale here. This is like 0 seconds to 0.05 seconds. Immediately it diminishes, but you can still see a rather large audio component here. And as we continue on, it continues, right? So like as it's going further back, it hits like the seats, it hits the ceiling. That ceiling reflects off of more seats. Those seats reflect off the wall and they eventually hit your ear. Let's say down here, right? Like down here at whatever, the 2.4 second mark. So this is simulating all of those acoustics that bounce off of things and hit your ear. If you've ever gone and done karaoke, this is what they're doing to your voice to make it sound like it's good. They're putting some reverb on it. So what does this sound like whenever we apply it against gymnopede D? Maybe I got that right. So if we move this signal, we're effectively taking this impulse response and running it across this whole thing, right? So at this point we say like, oh, this point is going to be loud. Again, this is, What I actually need to do with this track is reverse it, because that's how convolution works. So if I go to effect and reverse, there it goes. And then I will zoom out so that we get a better picture, right? So this starts playing, and then we hit that initial impulse response, which is like, okay, this is the true audio signal. This is the audio signal without being applied with like any echoes. As we continue on, the audio signal from just a moment ago is replayed again, but smaller and smaller and smaller and smaller, but maybe bigger this time because a wall made audio reflect in a way, and then smaller, and then maybe bigger, but smaller and tiny and tiny and tiny. And so by the time we get down here to this 3-second mark, the audio from 3 seconds ago is playing again in your ear, very, very small. So that's what this is, and that's what we're working toward here. Luckily, we don't need to do any math to get this to work. They've already done all the hard work for us. So we have reverb. What we're going to do is reverb.buffer is equal to, surprise, we're going to use the await keyword here. And we're going to do get impulse buffer. That's the function that we have down here. This takes the audio context that we have, so audio CTX, and a link to the audio. In our case, this is going to be impulse.wav, which is included inside of your assets. So impulse, /impulse.wav. So what this does is it opens up the audio file, reads it all into memory as a piece of data, and it tells the audio context, hey, decode that piece of audio data and put it into this convolver. Now, any music that comes, or any audio, doesn't matter, it does any audio, not just music. This can't distinguish anything. So all of that will get fed through this impulse response and get played out, and all those tiny echoes will be added in automatically. So we will do here const reverb slider is equal to we'll just, in fact, let's just copy the one from high pass, right? Let's just do it. Actually, we don't need a slider, right? Because this is, you can't control the reverb. So we're just gonna do this. We're just gonna say this is the reverb, and we're gonna connect it. We're gonna say right here. Actually, we're gonna hook it up right after the gain node. Reason being, if we reverse engineer the scenario that we're trying to replicate, first, the audio is being played inside of the theater. It is the reverb of the theater is being applied to that music. The low pass filter of the wall is being applied to that, and then that's hitting my ear. So that should logically come after gain, before low pass. So we do connect of reverb. Reverb. There we go. So now, let's refresh. Oh. Buffer contained an unknown audio content type. Uh-oh. Did I misspell something here? I think I did. Yeah, this is create convolver. Reverb.buffer is get the impulse buffer, wait for this. And then, yeah, that should be fine. Huh. This, yeah, this should be okay. I'm confused as to what it's missing here. So if I do this, oh, the file is not found. Why is the file not found? It's, yeah, 404 and impulse.wav, and it should be there. It's right there. Oh, it's right. Sorry. It's assets/impulse.wav. I'm so sorry. That's a total miss on my part. Assets/impulse.wav. There we go. Now if I refresh, there it goes. There you go. And you can already hear that reverb immediately. So now if we apply low pass filter to this, move this all the way down to the super low area. That's it, right? If you close your eyes, you're like right outside of the theater, right? Like you can hear someone in there warming up on the piano, tickling them ivories, just going for it, right? Oh, that is cool. Yeah, it is very cool. H Mendoza, it's awesome. But let's say that maybe I want to control how much reverb there is, right? Let's say that like I love the way that this sounds, but maybe I want some like a little less reverb. How can we accomplish that? We've already got the tools at our disposal, actually. So I'll turn this down. Here's the chain that we have. We have our input, connects to our gain node. In fact, I'm going to turn just that sounds. I love when I get to this part because everything just sounds so nice. I am going to turn it back up just because I like the way it sounds. We have our input, connects to our gain node, connects to reverb, goes to low pass, high pass, analyzer, and then all the way out to destination. What if we had the audio split at a point? What if the audio connected to not just, what if this gain node connected to not just the reverb, but it also connected to one that didn't have any reverb? And then we could use a slider to slide between having reverb and not having reverb. That's how we can control how much reverb we want to hear, right? If I want 80% reverb, this will be the signal that we're listening to right now. 80% of that plus 20% of no reverb. So that's how we can accomplish this. So let's start adding some sliders, baby. So let's do this. Const no reverb is equal to audio CTX dot gain node, right? So we're going to create a gain node here. Mind blown. Yes, exactly, Mia. We've got the tools. We've got the technology. We can make him better, smarter, faster. Const yes reverb is equal to audio CTX dot gain node. Now we're going to create a slider. Just like we did before, we're going to take this exact same concept. But, right, because we're going between two different values here, or between two different audio experiences, we're going to model this as a percentage. So 0 to 1 and some decimal here. So because this is what's going to be feeding into the gain node. So the gain nodes, plural. So 1.0, and we're going to name this reverb and reverb because that's what it is. There we go. 0 and 1, and our default is going to be 0.5, and our step is going to be 0.01. And this is going to be our reverb slider. So we've created our slider. Now we need to do our input. And the way in which we're going to do this is I just copied the one from high pass slider, replace the variable name. Whenever reverb slider changes, what we want to do is say our no reverb, right? That's our gain.value is equal to 1 minus reverb slider, right? .value. Reason being, if I have the reverb slider all the way up, I don't want to hear anything from the no reverb. I only want to hear yes reverb. I said, I've got a fever and the only cure is more reverb. And then we'll do yes reverb.gain.value is equal to reverb slider.value. So as the reverb slider goes up, our reverb goes up. So that's what we're doing here with these two gain nodes. Now, let's hook everything up, right? We have these gain nodes. So this source node is hooked up to this gain node. It's then hooked up to reverb and then up to low pass and high pass. So this is logically where we need to do things. So if I hit enter, source node is now connected to gain node. What I can do now is say, gain node, I want you to connect to straight up a signal that's called no reverb, right? Excuse me. sorry, this is .connect, connect to no reverb. And then that no reverb is just going to hook up to the rest of it, right? So we will just copy and paste everything that's down here. So gain node, connect to no reverb, which connects to low pass, high pass, analyzer, and audio CTX. Down here, we want to connect gain node to reverb first, and then to yes reverb, right? So what this does is that one gain node, remember I said it can connect to, like, it's got one output, but that one output can connect to multiple inputs. So this gain node is now feeding its output into our no reverb whole line that's doing its whole nasty thing. And then it's also connecting to reverb, which also connects to yes reverb, and then yes reverb connects up to low pass, high pass, analyzer, all that stuff. Does it have a semicolon on each line? It doesn't need one. Fun fact about JavaScript is that it doesn't care if you put a semicolon anywhere. JavaScript is the Wild West of programming languages, almost as bad as PHP. So basically they say, I don't know, what are rules? So let's see if we did this. Let's see if we did it. Give it a refresh. Doesn't look like we did. Audio CTX gain node is not a function. Oh, sorry. Audio CTX dot create gain. Create gain. Yes. So replace these two lines with create gain. There we go. So now if I'm not mistaken, if I go reverb all the way up, we should hear reverb. There's reverb. All the way down. And there it is. That's it. So that's how you can create a reverb slider, right? And you can do this with any effect. So you can have whole branches, right, that are just like, I want to take the audio and I want to apply these like weird set of transforms to it. I want to low pass filter it. I want to high pass filter it. I want to just get like the set of frequencies that are in the mids, things that, I don't know. I want to get the frequency range of just the theremin. And I'm going to filter out everything but the theremin inside of this song. It'll get the theremin and other things that are in that frequency range. It doesn't matter. So you apply that, and then at the end of it, you stick a gain node, and now you could turn up and down the theremin independently, right? Like anything inside of that audio range, you can turn up and down. So gain nodes are very useful, not only for just like increasing and decreasing the volume of the source, but increasing and decreasing the volume of your effects as well. So yeah, that's reverb. What I showed you inside of Audacity is being applied inside of JavaScript every moment that it can. It runs for every bit of audio that's coming in. It does all of the math, convolution, integrations, calculus. It's big brain Jimmy Neutron time. And it does that all the time, right? And we don't have to do anything. We just told it to do it, and it does it. So, last thing that we're going to do is we are going to go and take a look at the JavaScript Web Audio API docs. So if you ever wanted to get into looking more deeply at the JavaScript Web Audio API, the MDN Web Docs has a really well-written source on all of this stuff. So you and I together are now going to use the MDN to add panning to this, right? Because I'm sitting at a cafe, I'm hearing this sound. It's not coming directly at me on both sides equally, right? Like I'm at a cafe, the place is over there. So like, let's put a panner on it, right? So let's take a look at the MDN and look at the panner node. So what does the panner node have in it? This is what it does. Yeah, so it does this. It effectively pans the audio from one ear to another. This is the more simple way of doing it with just two audio channels, your left and right. But they've also got, if I come down here, they've also got some spatial audio panning that you can do, which is extremely cool. So let's take a look at this panner. So you've got a whole bunch of things here: distance model, orientation model, position. All of this is like, you set the position, you set the orientation. It's very interesting. This is the panner that's like general purpose. If I go to stereo panner, which says like, hey, I just want to do left and right, please, please don't make me think about anything. Now we have a thing that has dot pan, and that's what I want, right? Like our dot pan here, we just want to see, okay, there you go. Perfect. This value can range between -1 full left and 1 full right. So you know what we're going to do? Copy and paste. Correct. For everyone at home that just did Dora the Explorer and said copy and paste, you get a gold star. So panner node is equal to audioctx dot create stereo panner. Now we have our panner slider. Create slider pan, and pan here. Minimum value is going to be -1. Maximum value is going to be 1. Default value is 0, and our step is 0.1 is fine. So panner slider on input, we do panner node dot pan, not plan, sorry, dot pan dot value is equal to panner slider dot value. And now we take this panner node and we'll connect it right before, or sorry, right after our high pass node here. So we'll do connect panner node, right? And we make sure to put that on the reverb branch as well. Great. So now come back to our audio, give it a refresh. There's our pan. And now it's all my right ear. Now it's all my left ear. So we're going to turn the gain down. This is where the immersion happens. We're doing the mad science stuff here. So we're going to turn this low pass down way low. Right? We're going to get it to where it sounds. Yeah, that's pretty good. Yeah, that's coming out of that theater, right? We want that reverb cranked. Great. And now, again, it's not full face on me. It's not so far to the left that I can't hear it in front of me. It's probably about here. Maybe a little more. Yeah, there you go. So here I am. Theater is on the left. I've got my nice, warm, freshly baked bread. It is 1 p.m. I just woke up because I'm a degenerate. I'm eating my nice bread outside, listening to a pianist warm up inside of the Athene Theater. It is 74 degrees Fahrenheit in Paris, and I could not be more relaxed. Just close your eyes. You can hear the crinkling. You can smell the bread. You can hear people speaking French. And if you're more cultured than me, you can understand them. Awesome. So, while I play this, let's wrap it up. So, results are, this is a flexible tool set. This can accomplish a lot. If you are writing an article about let's say basically any subject. One of my 10 out of 10 want bread very badly. Thank you for the feedback, me. I appreciate that. If one of the articles that inspired me to start looking this up actually had a really immersive layout. It was talking about these this like crew of people that would go to shipwrecks and they would scavenge scrap metal, right, to take home and sell. And as you scrolled down through the story, like the sounds of waves would come up, the sounds of seagulls, the sounds of people with hammers, right, like at different parts of the story. different audio effects would be playing. And I thought, wow, that's like a really useful tool in a storytelling thing. So not only just for games or doing live streams or anything like that, you could also do this with like written word, just to add that little bit more of immersion. And this works with any browser compatible software. The Web Audio API has been in here for a long time. It's just that no one uses it. And this perfectly simulates a very mundane vacation. A lot of people say, like, I would love to go to Australia and ride across the outback in like a Jeep and go camp out in the wilderness. And, I want to go climb the mountains. I want to go bungee jumping. I just want to eat some bread. I just want to eat some bread and listen to a piano and feel like I can breathe again. So, I have a full demo of this that you can go play with right now if you want to at webaudionemo.codingvibe.dev. You can add your own filters programmatically and play them in the browser. You can also play with any audio source. So if you just slap in the link to any stream, any static MP3 file that has cores going for it, you can play with this all you want. The source code for that is actually inside of Web Audio API demo, that repo inside of GitHub. And I also used a lot of the principles that I learned in researching the Web Audio API to build Lazy Day Cafe, which is a pixel art immersion experience, sort of like Lo-Fi Girl or the Chill Hop live stream, just to sort of give you something to like listen to in the background and immerse yourself in. So it uses some WebGL shaders. If you're interested in that, you can go check that out. So if anybody's got any questions, now is the time. I love this audio, and I love the way that this has turned out. So any questions, any suggestions, anything that anybody wants to do, I'm going to quickly pull up the Web Audio demo. I'm going to mute my perfect, a beautiful project here, and I'm going to, let's add a gain node here, do this. So this is just a lo-fi radio station, and any of the things that we added in this demo, you can add at any point. These are sequential, so you can do low pass, high pass. The reverb thing is already programmed into this, so you can add reverb, you can add a low pass filter after, you can do a pan after that, a high pass after that, whatever. All these will work, and you can remove them automatically, and it all works too. So you can upload the local file, whatever. So yeah. If there are any questions, let me know. If there are any questions that you have while you're watching this on YouTube later, feel free to tweet me at CodingVibe or stop by my stream. I stream 3 days a week, Tuesdays, Thursdays, and Saturdays from 9 till 11. Approximately. There are times where I stop streaming at 1 a.m. because I'm having a little too much fun. So check me out on any of those places. Take a look at my GitHub repo for any of the projects that I built on stream, including this. And I hope that you had a good time. I hope you learned something. And I hope that the next time that you want to go to France and eat some bread outside of a theater, you just unmute this browser tab and you say, Thanks for watching, everyone.